So let me give you the following transition matrix. So 0.2, 0.3, 0.5, 0.4, 0.6, and then 0, and then 0, 0, 1. Okay, and then we could be asked, you know, is this Markov chain regular? Okay. So one thing to note is that, okay, so I've only told you the transition matrix. Technically speaking, just knowing the transition matrix isn't enough to have a full understanding of the Markov chain, but it is enough to determine if it's regular. So we don't really need to know the initial matrix, the initial state matrix. Okay, so we're going to analyze this the same way as before. So P has the kind of pattern plus, 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 right? All of these are positive. Plus, plus, 0. Okay. And we're trying to determine if there's some power of P that is all positive. So just like before, let's just try to take the square and see what happens. Okay, so so we just kind of go, okay, we say first row times the first column. Basically, we see a plus in the first, like the first entry here is a plus and that one's a plus. So we don't really need to care about the rest of it because we're just going to, yeah. Like since that's a positive and that's a positive, and then if we keep going, we'll just be adding zeros or adding positives. So it doesn't really matter. So yeah, that means that this entry is going to be positive. We take this row times the next column. This already means it's going to be positive. And then it's going to be positive again. Okay. Now we do the same thing with the second row. First column, it's going to definitely be positive. Actually, you can kind of see just because of this entry, everything's going to be positive here. Okay. Last row is a bit of a different story. So I take this last row times the first column. I go 0 times positive is 0. 0 times positive is 0. Positive times 0 is 0. So it's still 0. Exactly the same thing happens on the second column. And on the third column, we get a plus. Okay, at this point, we still can't say anything about this because it could be it could be regular because maybe if I take P cubed, maybe it's gonna be all positive. We can't really say at this point. So let's analyze P cubed. So P cubed is the same as P squared times P. P squared had the form plus, 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 0, 0, plus. And then P was similar, but it had another 0, so it was like plus, 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 0, 0, 0, plus. Right? And now we do the multiplication. Okay. So again, well, maybe I'll just kind of write this down quickly. But hopefully you can see how this works. So the last row, it's again 0, 0, plus. Okay. Now at this point, I actually can say Like I can just say, okay, this thing is not regular. Now the reason for that probably isn't clear right now, but I don't know if, can anyone see why somehow by analyzing p, just looking at p, then I look at p squared, then I look at p cubed, and now I can say, yeah, we're never going to get, if we take p to the 4, p to the 5, we're never going to get all positives. Can anyone see why? It's just going to keep coming back to the same matrix over and over and over. Yeah, that's exactly the point. So the reason it's not regular is because p squared is the same as p cubed, and it contains zeros. Obviously, if p squared was all positive and it was the same as p cubed, that wouldn't be a problem. But yeah, so p squared is the same as p cubed. Now, if I think of, like as was said there, like so that's the right idea. That if I now take p to the 4, that's just the same thing as multiplying p cubed times p. But that's the same as, because p squared is the same as p cubed, it's the same as multiplying p squared by p. So basically the same, so basically we get a, so anytime you get so this is kind of a fact. A repeating pattern that has zeros in it, then it's not regular. Okay. You know what I mean by repeating pattern? All I mean is like here, when you get something, some power of p is the same as some other power of p, right? Then that's what's going to happen. Any questions about that? Okay. Let's do another example like that. So, which is a little bit, kind of a different type of repeating pattern. So, I'll just change the entries of this matrix. Okay. So everything's kind of similar, but actually maybe I'll give you guys a few minutes to think about this one. So, okay, so I can tell you it's a bit of a spoiler alert, but this one isn't regular. But basically what you should be trying to figure out is how can you justify that this is not regular? So maybe do a few of these calculations and see what happens. And feel free to talk amongst each other. So I guess the question is it regular? And then why or why not? don't mind me, I'll just start writing another example. So does anyone already have a reason why this isn't regular? Yeah. Yeah. Yeah, so exactly. So turns out if you start taking powers, you'll find. So did everyone get this for p squared? Hopefully it looks something like that. That's what anyway, that's what p squared is supposed to look like. And then you go to p cubed, and as you said, the pattern just kind of keeps flipping back and forth. So it'll flip back to this, right? And then at that point, you know that, so like it's just basically flipped back to the same pattern as p. So you know that if you take p to the 4, what's going to happen is you're just going to see this pattern again. Then p to the 5, you're going to go back to that pattern. P to the 6, it's going to go back to that one. So it just kind of oscillates back and forth. And actually, and sometimes it might just seem like a little trick for finding out whether things are regular or not, but like this is, if you have a matrix where the Markov chain is not regular, this will always happen. There'll always be some kind of repeating pattern that eventually comes back. And so, yeah, so this is the way to show that something is not regular. You know, do a few powers, and then hopefully you see a repeating pattern. So you don't have to take all the powers off to infinity, because yeah, that'd be impossible. Any questions about this stuff? Okay. Let me, so I was writing an example here, but before that, let me mention an interesting fact. And okay, it's interesting to me, but you might not find it that interesting. So if P is the transition matrix of a regular Markov chain, then if I keep taking powers, like I take p and then p squared, p cubed, dot, dot, dot. So imagine we take powers kind of forever. So each of these will be like a k by k matrix or whatever. So each of these is a matrix. And basically, if you look at the values in the entries, they all kind of get closer and closer to a certain value. So what I mean by this is, so this sequence converges to a matrix. So we haven't really talked about what it means to converge, but when I say it converges, I mean the entries in that in this matrix get closer and closer to some certain value. Well, so it's something called the limiting matrix. Which we write as P bar. So P with a bar on the top. And every row of P bar is equal to the stationary distribution. Okay. So we'll give an example of this in a minute, but but basically what you should think of is, yeah, if I take, you can try this in actual examples. Like take a regular Markov chain, take powers, bigger and bigger powers of that matrix, and you'll see that the values get really close to, like in the first row, all the values will be like really, really close together if you take a really high power. And the number that they get close to is the first entry of the stationary distribution. So kind of magically, if you take high powers of this thing, it always kind of looks roughly like the stationary distribution on every single row of the matrix. And like I said, we'll give an example here. Okay, so I'm going to do an example now that's going to put together a lot of different things. We're going to do a word problem, turn it into a Markov chain, and then analyze the stationary distribution, limiting matrix, and stuff like that. Okay, so here's the setup. You've got two boxes. One of the boxes is red. One of them is green. I feel like you probably had a bunch of MyLab math questions. Maybe they called them urns. I don't really know. I don't feel like people put balls into urns, right? But anyway, so that's why I'm calling them boxes. So two boxes. One is red, one is green. The red box has two red balls, two green balls. The green box has one red ball and two green. So we randomly select a box, and we remove a ball. And then what we do is we put that ball back where it came from, so we don't move it to the other bin or anything, or the other box. So when we put it back, and remove a ball, and yeah, from the bin or the box of the same color as the ball we removed. Okay, and then we just kind of repeat forever. So I'm not sure if this is clear. Probably not. Okay, so this is our situation. We first just say, we just go, okay, 50-50, or flip a coin, pick one of these boxes at random, take out a ball. So suppose I pick the red box, I take out a ball, and suppose it's green. Then next time, then I put that ball back, and next time I pick a ball from the green bin. And probably, I mean, it's more likely to be green, right? So when I pick it from the green bin, maybe it's green. I put it back. I pick from the green again. Maybe it's green again. I put it back. And then maybe I pick from the green again, and I get a red. And then it switches. I switch over here, and I start picking and putting them back, and so on. So that just repeats forever. Okay. Is the clear? It's a very weird thing to do, but okay. So what I want to do is express the choice of box color, or yeah. I guess in each round in terms of a Markov chain. So is the setup clear, or are there any questions about it? Okay, so for this question, like, the choice of box color in each round is either going to be red or green, right? So I've got two states. Red or green. So what I need now, well, actually, what do I need? Like, how do I express this as a Markov chain? I definitely need that. And I actually need one more thing. Yeah, the initial state matrix, yeah. So let's start with the initial state matrix, because it's kind of easier in this case. So in the question, it says that in the first round, all you do is just randomly pick one of the bins, like kind of 50. It doesn't say 50-50 here, but you can kind of, I mean, that's what I meant by randomly select a box. So the initial state is just going to be, on my first round, I have a 50% chance of picking the first box, 50% chance of the second box. So your initial state should always be like kind of indicating what happens in the first round. Like how does the first state get determined? And here we said the first state gets determined randomly. We randomly select a box. Okay, our transition matrix. So we're going to want, so suppose I'm picking from so my current state is red, which means I'm picking from the red box. What's the probability that my next state is red if I'm picking from the red box? Yeah. Yeah. I'm actually going to start writing this as, I know I'm kind of mixing up fractions and decimals, but it's going to become better to use fractions in a minute. And then we definitely know that, so this 0.5, or the 1/2, right, comes from the fact that if my current state is red, I'm picking from this box, I've got a 50% chance of getting a red ball, 50% chance of getting a green ball. Okay, and then this has to be a 1/2 as well. And then I guess I've got a 1/3, 2/3 chance. If my current state was green, only 1 out of the 3 balls are red in the green box. Okay, so that's the matrix, and those are the matrices. here's a question. What is the probability that the third box, box like the third box that we choose from is red? Okay. So this S0 tells me the probability that the first box is red or green, right? So how would I go from, so this tells me the kind of the first box probabilities, but like how would I get to the third box or even the second box? Any thoughts? So here's the kind of the key idea. So just to kind of break this down, S0 tells you, it tells us the probabilities for the first box. Okay. We want to know the probabilities for the second box. Yeah. You could do a tree. That will work. Yeah. Just because we're kind of using a different perspective in this part of the course, we're thinking about Markov chains. I'm going to do this kind of by writing certain matrix multiplications, but in principle, there's nothing wrong with your answer there. That a tree diagram would work. Yep. Well, yeah, kind of, and and then you want to also multiply by this initial state matrix as well. So if I take S1, which is S0 times P, this tells us the probabilities. So you wouldn't, if you're doing this, you wouldn't have to write all of this, but this is just to give you, to explain what's going on. And if you actually compute this, so maybe I won't do the matrix multiplication, but we've done a lot of that. I'm sure you guys can do it. S1 is 5/12 and 7/12. So that means, like for the second box, the probability of being red is 5/12. And then S2, which is S1 times P. But which you could have gotten by taking, so it's also the same as S0 times P squared, which I think, oh, yeah, actually, well, yeah. No, you do need to, yeah. You do need to multiply by the initial state matrix. Anyway, so this is going to be 29 over 72, 43 over 72. Okay. And this tells you the probabilities for the third box. So it has a 29 over 72 probability of being red. By the way, these numbers are roughly 0.416, well, so it's exactly 0.416 repeating and 0.583 repeating. This is not like, so yeah, this would be, by the way, this would be your answer to this question, 29 over 72. So these numbers, by the way, are roughly 0.40277 repeating, and then 0.59722 repeating. Okay, these numbers aren't so relevant right now, but it'll become relevant in a minute. Okay, any questions about this? Okay, so let's now find the stationary matrix. Okay, which is going to have two different, it's going to be a 1 by 2 matrix because I've got two states. So if we remember how to do this, we want to take, so you need S1 plus S2 to be 1. And you need S times P to equal S. Those are the criteria of the stationary matrix. Okay. S times P equals S just means, if I kind of expand that by writing the actual matrices, that just means this. Which is the same as a half times S1 plus a third S2 as my first. So I'm just doing the matrix multiplication. 1/2 S1 plus 2/3 S2. And I want that to equal S1, S2. Right? So then this system of equation, or these two equations can become a system of 3 equations involving these variables. So okay. At this point, I've got 3 equations, 2 unknowns. Does anyone remember what we can do at this point, like when we're finding the stationary distribution? Yeah, or matrix. Yeah, as long as you don't get rid of this first one, that's an important one. But yeah, you can get rid of one of these. I don't know. I don't see any advantage of one or they're kind of similar, so I'll just get rid of that one. Right. So then now I have a system of equations where I've got 1, 1, 1. For this equation, you've got to be careful because you've got variables on both sides. You want to get the variables all on the same side. So if I subtract over an S1, I'll have half S1 minus S1, so that becomes negative 1/2 S1. Oh, sorry, there's no S1 here in the matrix. Okay, so this negative 1/2 came from putting this to the other side, and you get negative 1/2 S1 plus a third S2 equals 0. So these are the same equation, right? And then I'll just say, like, I'll kind of skip a few steps here because we've done so many examples with Gauss-Jordan. But this tells you that you get 1, 0, 2/5, 0, 1, 3/5. So the stationary distribution is like 2/5 and 3/5, which is the same as 0.4, 0.6. Right? Because it says S1 is 2 over 5, S2 is 3 over 5. Okay, I kind of did that quickly, so are there any questions about that? Yeah. Yeah, so that's just taking this equation and then subtracting S1 over to the other side. And then it kind of, so what you get is like a half S1 minus S1 plus a third S2. If I kind of bring out an S1 from this, it's a half minus 1 S1, which would be a negative half. That makes, yeah. Okay, here's the thing. So okay, it's not easy to guess that it's going to be 0.4, 0.6. At least for me, it's not obvious that this should be the answer. But maybe if you when you do look at these first few, these first few states, like the initial state matrix, then you look at the next one and the next one, it kind of, the values are kind of getting closer to these 0.4 and 0.6. So we started at 0.5, 0.5. We then got to 0.4166 repeating, point whatever, right? And then we got to 0.40277 repeating. If you applied the matrix again, it's going to get even closer to 0.4 and 0.6. And then it'll get even closer and even closer. And so that kind of, I guess, justifies why this is the long-term behavior, right? As you apply this more and more, apply the process more and more, you're going to be roughly 40% of the time in the first state, so the red, picking from the red box, 60% of the time from the green box. Okay, any questions about that? Okay. So here's a question which is now, if you followed what I was saying about the limiting matrix, then this question, once you've found the stationary matrix, this should be very easy. Well, actually before that, maybe I'll give you two different questions that should be easy. So if this process runs for a long time, then what proportion of time do we pick from the red box, like in the long run? Yeah. Exactly, yeah. 40% or 0.4 or whatever. I mean, either of these would be acceptable, or 2/5, Right? And that's just because of this fact that we mentioned last time that, if you have a regular Markov chain, by the way, I should, well, maybe we need a bit of justification. So we should probably say, we never said that this is regular, right? So because this Markov chain is regular. I mean, it's definitely regular because all the values are positive right at the beginning. Yeah. No, that's a good question. Actually, I'm pretty sure all Markov chains will have a stationary distribution. But for some Markov chains, for one that's not regular, the stationary distribution doesn't give you this information. Yeah, I could be more precise than that, but this is not this is not meant to be a super deep math class, but basically, yeah, sometimes the stationary distribution won't give you quite the right information. Actually, more specifically, what I want to say is, if we run this for a really long time, then every single time we run the process, we should have about a 40% chance of being in this state. Whereas if you had something that wasn't regular, maybe some of the time you'd have no chance of being in that state, and sometimes you'd have, it would change as time goes on. Okay, so yeah, so the answer here is 40% because we just read off the first value from this stationary distribution or stationary matrix. Another question that should be easy now is what is the limiting matrix P bar? Okay. So I think maybe it's here. So for the limit, if you have a regular Markov chain and you take the limiting matrix, the key thing is every row should be equal to the stationary distribution. So if you just kind of memorize that, if you know the stationary distribution, you can just write this down. It's just write the stationary distribution, write it again. If it's bigger, then you write it again. Just keep writing the stationary distribution. Any questions about that? Yeah. Yeah, so, well, because it's kind of asking a different question. So it's trying to say, if I take p and then p squared, p cubed, dot, 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 forever, then what we're trying to say is that this will eventually get to a matrix that looks, like if you do this 1,000 times, the values here are going to be really close to these values. If you keep taking powers of p, it's going to be a 2 by 2 matrix. It's not going to be a 1 by 2 matrix. So that's why you have to write it twice, because it's, yeah, if you keep taking powers of p, it's still 2 by 2 forever. Okay, so this is everything about regular Markov chains that I wanted to say. So next we're going to look at a different type of Markov chain, though, which has a kind of funny property. Maybe I'll just kind of introduce them quickly now. And maybe I'll just introduce them with an example. Suppose P is the matrix okay. And here's my question. What is the long-term So this is just kind of testing your intuition here. So let's say I've got a Markov chain with this transition matrix. And my question is, what is the long-term behavior? And I guess I'm kind of asking for this kind of in words in a sense. Okay. And in this case, I don't really care where the initial state is, but actually when we do more complicated examples, we will care. It'll be important where the initial state is, but for this one, it doesn't matter. Yeah? Yeah. Yeah. Yeah, I think you got the right intuition there that like this, so this may, let's say the states are A, B, and C or something. Maybe at the beginning you'll jump around between A's and B's and things like that. But at some point, if it ever jumps to C, now you're in an infinite loop. Like you're just gonna, because if you go to C, you're just going back to C. You're gonna get stuck there forever. So it eventually, it basically gets stuck at C forever. Okay, this is kind of like this. actually, we did an example about gambling where someone came in with $2 and they would either go down by 1 or up by 1. And when they get to 0 or 4, they stop. That was kind of similar to this example in some sense, that you either get stuck at 0 or stuck at 4. But what we're going to do, we're going to look at examples where you have multiple different states where you could get stuck, and you want to know what's the probability you get stuck there versus the probability of getting stuck there, and that kind of thing. All right, so